Brianna with EMU. We specialize in the Pass Bus standard, both training and services related to that. And we may just, pop in every once in a while and add our little tidbits for Steven here as well. But, we'll be here for Q&A afterwards. And then this is Mark.
I'm Mark with Hammerwell, and I'm a builder. I know something about mechanical systems, but I've learned most of it from these two, so I'll comment if necessary.
And it's after lunch, so feel free to throw in questions. Let's keep it a little interactive so we can keep it moving. I have 21 slides to go through, so I have a bunch of stuff. But don't ask any question you want at any time. We're on that. It's going to be that one. Why is it not moving? So, yeah, I'm Steven with DMA Engineering, principal engineer. Our involvement, we specialize in net zero projects. It's not our passion, but also our genius. Mechanical systems are the largest user of energy on site for residences and buildings, so their main consideration. Three main considerations are key for success for projects. Owner's requirement, you got to understand what the owner's trying to achieve with their house. So we do a client intake form, and we never, like thermostat set points, right? Industry sets those what they're supposed to be. We never see anybody want to do those. We've seen clients that want 72 for heating and 68 for cooling. We see it all over the board. If you don't ask that question up front and you get to the end, you cannot meet those requirements if you're using them for what's standard per code. Noise. Noise is another issue that pops in. We build really, really tight houses today. The ambient noise from outdoors doesn't come into a home and you don't hear it anymore. So now all the stuff that's inside the house makes a lot more noise, and clients are a lot more sensitive to that. So you want to know what their noise sensitivity is. It may actually change the mechanical system you choose at the end of the day. The building envelope. Make the mechanical systems as small as possible. I have 3 slides as a mechanical presentation on the building envelope, and then cite the constraints. Can you put in a ground source heat pump system? Do you have anywhere to put the wells? How much solar are you going to be able to get to offset the energy from the mechanical system? Do you have enough solar aspect? What are you going to do about that? You're going to go to Jack's Solar Garden to meet the Boulder County or the city requirements. Those are the type of things you need to do. Design through final commissioning. Our contracts are written so that we stay with the project 9 months after the homeowner moves in. The days of setting a thermostat and going and leaving, you should have all your mechanical contractors' contracts should be to hold some money back for a certain amount of time until the system has actually gone through two major seasons, a summer and a winter season. There's just so many things that happen with complicated mechanical systems that take some tweaking to get dialed in. Expectations of homeowners are starting to increase greatly, and we're seeing more and more people just have different expectations once they move in that things need to be tweaked in. And I'm not saying this is a warranty period. Warranty is if something fails. This is actually there to make sure there's little small tweaks with the mechanical systems. Next slide, yep. So building envelope. Insulation is cheaper than heating and cooling systems. Keep that in mind, it's always important. Windows double and triple pane glazing costs have come way down. In 2013, we did a 13,000 square foot net zero home. The windows that we went with were the Alpine, I don't remember the exact series, but they were, 0.19 solar heat gain coefficient, U value of 0.2, over a standard of 0.3 U value and a 0.3 solar heat gain coefficient. It was a 2x for those windows. Today, that exact same window, not the exact same, but one very similar, it's only a 10% increase. So in 9 years, the window cost has come down significantly. Why would you just not do that window? Infiltration, code says 3 air changes per hour per 50 pascals. I have a email blast that goes out and says, don't be a weenie, don't do 3 air changes per hour at 50. Come on, we can do better than code minimum. So 2 air changes per hour at 50 pascals. It's pretty easy to get there, right? A little bit building details, take care of some things to get there. 1.25 air changes per hour at 50 pascals. It's getting kind of hard, especially on the big houses that we work on. It's kind of, it's difficult to do. 0.6 air changes at 50 pascals, which is the certified passive house. Take EMU's certified passive house tradesperson, because that's difficult. There's details you got to watch out for. A better building envelope results in a more comfortable residence. And the reason I say that is if you're standing next to a window that is hot and your body is absorbing that energy, you're going to feel hot, right? If in the reverse, if that window is cold and you're hot, you're giving energy to the window, you're going to feel cold. To make that up in a mechanical system, in a forced air condition, I have to supply more air. So now you got more air that's running through the house. You've got all these different things playing together. You got a very dynamic situation. But if that window is closer to room temperature just naturally, I don't have to move as much air to overcome those. You're going to feel much more comfortable in the space. Next slide. So the building envelope. So this is we do what's known as a life cycle cost analysis mixed in with the trade-off analysis. We use weighting factors to kind of get there. So with this particular one, we did 1 inch of exterior insulation. The insulation on its own would never pay back. Just never would, right? Law of diminishing returns over what the code minimum is. But, so we do a trade-off analysis. One thing that we do in ours is occupant comfort, which is based upon the operative temperature, which is out of ASHRAE 55. Gets really complicated. I will not get into that in this presentation. But we look at occupant comfort based upon operative temperature of the room. Then we do some architectural impacts, construction impacts, but then the HVAC impact. So what is the impact of adding 1 inch of insulation on the mechanical system? This says, the way we have it in this particular house, it's going to knock down the tons of the house by 3. So it's going to take it from, 10 tons to 7 tons, I think is where it ultimately ended up. We say that for each ton of HVAC is $5,000. So that's $15,000 savings right there off that. The 1 inch insulation was $32,000. Financial impact, we have a thing in there, and then the environmental impact due to the carbon, it's another way we do our weighted averages. But that's not the whole story. This is in the Boulder County, has to be a net zero residence. So how much solar does it take to offset that from going from code minimum? How much does the 1 inch knock off of it? It's actually 5 kilowatts. Use $3 per kilowatt, that's another $15,000. That's $30,000 the insulation just paid for itself. So you can't just look at it on a straight payback. You have to look at it holistically. How is this actually changing what's going on? 3 tons of HVAC is a lot of HVAC system. Next. Very good. Next slide. So mechanical systems, standard furnace and DX cooling, or DX cooling and boiler. Every builder is familiar with these type of systems. This is the standard that's out there. Gas is as efficient as possible. We cannot combust gas any more efficient. So a 95% efficient furnace, that's the maximum we can get out of it. I was at a boiler manufacturer several years ago, and he goes, there's no more efficiency to be gained, right? So that's all we can get out of a boiler is like 95% efficiency out of it. Controls is where they were headed with their designs. DX cooling is getting super efficient, and we'll kind of get into that when I start talking about heat pumps. But everybody's familiar with DX cooling. That's pretty much standard what's in your house. Forced air cooling is that way. The advantage, lots and lots of contractors know how to install and service these systems. So there's a momentum of change is coming along with that. So mechanical systems, all electric, no gas. This is the future. This is where we're headed. It's being forced upon us by code. Denver is going this way. Boulder's going this way. The industry is just pretty much going this way. So they'll be all electric, no gas, but straight electricity can be expensive. Gas is approximately 3 to 4 times cheaper per unit of energy. That changes a lot. I've been tracking this for the last 15 years, and gas prices are all over the place, but right now I think it's about 4. So electricity is getting easier to do because of the way the gas is coming once we get to heat pumps. So let's talk about what coefficient of performance is, a unit of work out for a unit of work in. So when I said a 95% gas efficient furnace, for one input of energy you get out, you're getting 95% of that back out. So in a COP, we would say it's a COP of 1 and a COP of 0.95 on a gas furnace. Specifics, you can do electric baseboard, electric strip heat, electric boiler, and then you got heat pumps, air source, and ground source. So electric baseboard, right, it's a COP of 1, on-off, no modulation. There's a lot of houses like in Evergreen that are all electric. We actually are looking at a project right now that they use all electric baseboard, and they're really, really expensive. They're considering changing over to a ground source heat pump system, but it's hard to do in a retrofit application. Then you can just do electric duct strip heaters. Pretty common, COP of 1. You can modulate these. And then you can do an electric boiler. So you can do again, it has a COP of 1 modulation. One advantage of these is they don't drop in efficiency at higher water temperatures, where a gas-fired boiler does lose efficiency at higher water temperatures. So we can do right now, you're fine, we can do everything a gas-fired boiler with electricity. The COP is just 1. Financially, it costs a lot of money to heat just with straight electricity. So you don't want to do that. So we use heat pumps. And so heat pumps are the future. This is the cool stuff. So it's a high coefficient of performance, a COP of greater than 3. So the economics are in current line with natural gas costs, making them competitive. We can do everything with the heat pump that we can do with the gas-fired boiler and air conditioning unit. We can do radiant technologies, domestic hot water, spa heating, swimming pool heating, and snow melt. So what is a heat pump? Don't be scared. We don't have a lot of older folks in the room, but so everybody knows what a heat pump is because everybody has a refrigerator in their house. And all a heat pump is a refrigerator. It's that simple. It just depends on what part is the hot part and what part is the cold part is the only difference in a heat pump. And there's a little magic valve in there called the reversing valve that just changes what part is the hot part and what changes is the cold part. So it just uses a refrigerant, compressor, an evaporator, and a condenser. So there is essentially 2 different types of air source that are currently on the market right now. We have air source. The cost is 1.2 to 2 times more than a conventional system. And I actually think that cost is coming down a lot. I don't think it's that great anymore. And this is I just put these together a year ago. Ground source costs 2 to 3 times more than a conventional system. That's just the way it is, and we'll get a little bit more into why that is. So air source, air-to-air split system. This looks just much like a furnace, right? So it's your standard air conditioning unit. That's exactly what this is. There's just no furnace with it. No gas-fired furnace with it. So they're much like a conventional system. I'm not going to get into all the COPs and the AHR rating. The thing that's coming out now is heating seasonal energy efficiency ratio. It's like the SEER. So you'll hear those numbers. Just keep in mind that the higher the heating seasonal efficiency ratio, the more efficient it is, just like your SEER rating that you hear now on your conventional AC units. Us as engineers, we really don't look at any of that. We look at the COP numbers. We do our energy modeling. We put the actual COPs and the capacities into our energy modeling software and run it that way, so we're getting the actual performance out of it. The SEER and the seasonal HSFPF are meant just to be very quick ways to look at it. I think the HERS models may use those numbers versus the COP numbers. I'm not that familiar, but I think that's what they do. The disadvantage of these particular systems is they lose capacity at lower temperatures of 17 degrees F, and typically you need an electric strip heat for backup on these type of systems. But they can be ducted much like a standard furnace, and rebates exist. One big advantage, your standard AC guy is going to know how to install these, right? This is nothing that's outside the normal for what they can do. They're just not as efficient as some other technologies that are there. So now we get into the heat pump system, the mini split systems. Sean with Mitsubishi is here. This is Mitsubishi equipment. The biggest thing with these is they're inverter driven. So you can do load matching with them. There's a lot of efficiency with these type of systems. They have high capacity at lower temperatures. So they're rated, Sean was standing here, you may be able to correct me, but I think they're 80% at negative 13 degrees now, or they may even be 100% at negative 13. I don't remember the number, but they don't lose a lot of capacity. We actually have one of these Mitsubishi systems installed in a project at Estes Park with no backup, and we're at 9,000 feet. We had no problems with the house, this is a commercial building, it's a bunk house at the Eagle Rock School. No problems with the house in the last cold snap we had. So no problems with it. Lots of options for the indoor units. All these things over here are the indoor units. So there's lots of flexibility in the design. We can, you could do the standard wall mount unit that you see in a hotel room. You could do a cassette in the ceiling. You can do a horizontal ducted unit, and then you can do the little pancake units. We've been using a lot of the little pancake units because we can put them in like closets and access them that way, and then duct into the rooms where we need to. So that's kind of been the one. I think we just did a house in Steamboat where we're using a lot of those. And then they have a higher EER in cooling, so there's a lot of efficiency with these type of systems. And then we can do an air source heat pump, water to air. So this replaces a boiler. So we can do forced air heating and cooling with this. We can do radiant floor heating and cooling. Very flexible in the design. Most of the designs that we do at DMA Engineering use a typical air-to-water or water-to-water ground source heat pump systems due to the flexibility in the design. Allows us to do a lot of cool stuff. And then you can do swimming pool and spa heating. So, I mean, you don't have to have any sacrifices with electric heating from using a gas-fired boiler. That's kind of the point there. And the COP does disappear a little bit at higher water temperatures, and I'll touch base on that when we get into ground source heat pump systems, a couple of things to consider. All right, so ground source heat pump systems. Now, this is the stuff that I like. I really like ground source heat pump systems. This is currently the highest efficiency system that you can put in. They are expensive. That's why you don't see a lot of them. Air source efficiency is increasing, but you just can't beat what the ground source heat pump efficiency is. You just can't. You won't get the same efficiency out of it. I'm not going to get into the HRI rating. There's no electric backup required with these. You can get 100% of the capacity, much like you can with the inverter driven. And the tax credit is currently available. And with the Inflation Reduction Act, the tax credit went from like 26% back to 30% for the next 10 years. So that's a huge thing with these when you're looking at the economics of it. So then you can do water to water, replaces a boiler. Again, I'm not going to touch base on the COPs. You can do radiant heating, cooling, pool heating, spa heating, snow melt. And then lower water temperatures in heating than boilers. Design is a lot more sensitive. So when somebody says that a ground source heat pump system or an air source heat pump system, water to water, they have issues with it, it's typically a design issue. It's not a piece of equipment issue. Something got messed up in the design. Somebody didn't overlook something. And the reason that is a pipe is typically undersized, and we can't push enough energy through the pipe because it's just not sized for the right flow. If this happened in a boiler scenario, the mechanical contractor would walk into the mechanical room and change the set point from 140 degrees to 170 degrees, creating a bigger delta. He gets the same amount of energy, and he goes home, and there's no problem with it. You can't do that with the heat pump. Heat pumps have a higher upper limit on them at about 115 to 120 degrees that you can get out of them. Some can do higher than that, but typically it's that 115 to 120. If you're already pushing 115 degrees and you've got a pipe that's too small, you're never going to get the energy out of it. So design is a lot more sensitive when you're doing a heat pump type design, when you're doing water to air or water to water type systems. So then the ground source heat pump system plumbing options. You can do a vertical collector. This is like what's known as a slinky design. Don't ever do a slinky design. Ground, horizontal, and a pond type system. So if you got water, surface water on your project or in your development, great idea to think about using one of those type of systems. And you could do a little bit of a district type ground heat exchanger. Horizontal collector. If you're moving dirt on site, you got to be thinking about putting in a ground heat exchanger. We're working with a developer up in the Roaring Fork Valley. They're building this big mound to block themselves from the highway. And I told them, I go, anytime you guys are moving dirt, you got to think about putting in a ground heat exchanger. And they told me about this big mound they're putting in, this big retaining wall. And we did the analysis. We could have got 30 tons out of this mound that they're already moving the dirt for. It would have been an $8,000 investment to put in the tubing, and they would have been able to connect a 30-ton ground heat exchanger to it. It was too late in the process. They had already been so high. It was a missed opportunity. But 30 tons off of something that you're already doing, you just got to think ahead when you're looking at your energy projects. If we're moving dirt, can we do it? We have another project where they're going to move 10 feet of dirt we're going to put in a ground heat exchanger and they're going to put it back in. They have to do that for their soil requirements. It's going to be inexpensive to put in a ground heat exchanger. Verticals, this is typically what we see that goes in on a ground heat exchanger. I'm going to say a rule of thumb number. When you design with an air source or a ground source heat pump system, never use a rule of thumb number. Always do a load calculation. Always do all the math, because you'll get yourself in trouble by using a rule of thumb number. That's like the pipe size analysis I came back to earlier. Somebody says, oh yeah, you just do an 1.5 inch pipe and it'll be fine, when really it needed to be a 2-inch pipe. You get into problems. So never rule of thumbs. But typically, we do 250 to 300 feet per ton of ground heat exchanger. So if I was called out on site and you were like, well, how much is it going to be to do a ground heat exchanger? I'm going to be like, it's like this, and we can talk roughly about how much area you need. But we're not going to design to those numbers, right? We need to make sure all the math is put behind it. So that's that. What's that? Never these. And the issue is with the Slinky design, they were all the rage back 15 years ago. They were all the rage. The problem is the pipes stack on top of each other, and when they get filled, you get air gaps in them, and you lose conductivity. So you're doing all this surface, right, calculations, and you're saying, well, you're getting this. Well, you're not really getting the conductivity to the ground that you actually want, and we don't see the performance out of those that you think you're going to get. So take a holistic look at heating and cooling loads. Most houses are, the 3,000 to 5,000 square foot house, pretty straightforward house. A lot of the projects that we work on, are the 10,000 square foot, really large houses. And so you want to look holistically of where you can gain energy, right? So outbuildings, is there a garage? Is there barns that's going on with that? Pools, plunge pools, and spas. So one thing, we look at everything. How can we gain energy? So when you have a ground source heat pump system and you're heating the house or you're cooling the house and you have a swimming pool outside, you literally are, if you use one system to do it, take the heat out of the house and put it in the pool or spa. So you got to be looking at like those strategies on where can we gain energy and move it around within the project. If you're just looking at disparate systems, one system for the pool, one for the house, one for the spa, you're going to miss those opportunities. So you need to be looking at where can you couple your energy type systems together. Snow melt driveways and walkways. I used to be totally against snow melt. I mean, I talk people out of it. But a slip and fall, there's some numbers out there that says like one slip and fall is like $80,000. If you need to, heat a driveway, a walkway for somebody to get their car safely in the mornings, and it's, the aspect of it is that there's going to be there. If you do it with an air source or renewable energy ground source and you offset that energy, I'm not opposed to driveway snow melt. When we get into 10,000 square foot driveways, that's a whole different ball of wax, right? But if you're doing 100 square feet, whatever. So, all right, so then an ERV and an HRV. So an ERV is an energy recovery ventilator, and then you got an HRV, which is a sensible heating recovery ventilator. So typically in a residential application, you're going to be used what's known as a fixed plate heat exchanger, and it's one of these things over here, and it's got all these little micro channels in them. An HRV typically is made out of aluminum, and an ERV it can be made out of rice paper or a polymer. And as what happens, the difference between the two is that the ERV humidity, if it's hot, if it's humid inside your house and it's dry outside, as those two air exchanges go past each other, the humidity will go through the polymer or the rice paper, and it'll change and go back into it. So it's just trying to balance out the humidity between the two. So why do we do an ERV or an HRV? We do it because if it's 0 degrees outside and it's 70 degrees inside, and you have the exhaust out for like your bath fan. I have an email blast that goes out that says bath fans suck, right? So you shouldn't be doing bath fans. You should be doing an ERV. But the reason is that air is going out of your house at 70 degrees. You have to bring air back in to keep everything in balance. So when you bring it in at 0 degrees, you have to condition that from 0 degrees back up to maybe 80 degrees to deliver it to the house at 70 degrees. If you use an ERV or an HRV, that air that's going out at 70 and the air that's coming in at 0 are going to go through that heat exchanger, and there's a net energy transfer between it. What's leaving to the outside may be like 30 degrees. What's coming in is around 40 to 50 degrees. So now you only have to heat up from 40 to 50 degrees to 80 degrees to actually deliver it. So that's where you gain the energy balance between it. A lot of the houses that we work on, we will use they put in one of those 1200 CFM range hoods, right? You don't want to be doing that. It's good design, but they put in those 1200 CFMs. We'll put in an extra large ERV, and we can run the supply fan independent of the exhaust fan, and that we'll use this as our makeup air system. So we don't have to put in any type of other system to do it. We can just use the ERV to do it. We oversized the ERV to make that happen. So it can do that. But it replaces your bath fan, reduces energy consumption, increases indoor air quality. You can filter this as the air is coming in. Now you can put in pre-filters and all that if you're worried about smoke and all those other things, but it gets a little more complicated doing that. They do have a filter on them that you can do it. And you can keep turning the air out, right? So for passive house, you always have to have continuous air exchange coming in because the house, they're so tight, we need to make sure that there's good indoor air quality going on all the time. So we have to bring in a continuous amount of fresh air into the building. So the ERV allows us to do that efficiently.
It's worth noting to folks when you would use this, because when you get up to the passive house level, sometimes this is the only system you've got. You don't have any of that stuff beforehand. And you can explain that better why?
Yeah, exactly. I've totally spaced that out. I did it yesterday in the pre-run, but in passive house, you don't have a mechanical system. You have the ERV, and then you'll put in like a mini split system with the coil, and that's your heating and cooling system. So if you do a passive house standard, a lot of what I'm talking about is irrelevant, right? You don't really need that big of a mechanical system to heat and cool the house. That will be your system. There's a Zender system back there that they can give you a lot more information on that. All right. Well, I'm almost done. Well, I flew through that, I think. All right. So key takeaways. Good building envelope is key to a small mechanical system. And again, if you do a really good job and the mechanical system becomes irrelevant, from a builder standpoint, there's a lot of advantages to a really small mechanical system. Your callbacks will go down, right? Occupant comfort will go up. So you're not going to have as many problems that you normally have. It's cheaper, right? It's just cheaper to do installation over a mechanical system. We really like it on the big houses we work with. We want to make the mechanical system, they have a budget, and we're trying to get that mechanical system, the cost down, right? So we can do cooler stuff. So we can do radiant cooling, and we can do all kinds of really, fun stuff for us as mechanical engineers. But a good building envelope is key. Efficiency of the mechanical systems may need to be considered to reduce the offset. So like in Boulder County and the city of Boulder, you have to have offsets to what you're doing. So you're either going to have a really inefficient mechanical system and put on a ton of solar PV, or you can have a really good efficient mechanical system, a really efficient building envelope, and a small amount of PV. It's always that trade-off analysis that you have to look at holistically on which is the bigger bang for the buck. Look holistically, one size doesn't always fit all, and you should do a trade-off between the building envelope, mechanical systems, and renewable energy systems need to be considered. I mean, every house is different. I mean, you talk about just changing the orientation of a house, that the parameters are going to change. So you have to be looking all the time at holistically at the whole system. I think that's it. What's that?
Maybe I heard you wrong, but you were saying like tons. You were referring to the mechanical equipment in terms of like tons.
Yeah, so we talk in BTUs per hour, right? So 1 BTU per hour, the definition is to take 1 gallon of water up 1 degree F. I believe it's the true definition of a British thermal unit. So BTUs per hour is what we talk in. 12,000 BTUs per hour equals 1 ton, because that's the amount of energy it takes to, it's a certain amount of water to ice is 12,000 BTUs per hour, and that's how they came up with tons. So it's an old that yeah, that's just how we talk about it.
So like more tons is just more energy.
Yeah. So 1 ton's 12,000 BTUs per hour of cooling.
And passive house is similar.
Yeah, order of magnitude, that's a very good thing to point out. So order of magnitude, you're talking, you know, a ton is 12,000 BTU, right? And so it's 12, okay, so for passive house, it's 4.7 kilo BTU, so 4,700, 4,750
So it's less than
kilo
half
BTU
one
per
ton.
year, yeah, per square foot. Yeah, it's a big difference. So that's why he was saying when you get down to the passive house level, you don't need all that discussion about, you know, the heat pumps and such because you can get away with just using the ERV. That's your only system. So in some ways, it really simplifies things because you can just, like you said, insulation's cheaper, right? You focus on the insulation, conserve in your envelope, and use an ERV to meet your comfort standards. But if you don't hit that level, then you may need to compensate for your comfort level and for operability and everything else with some of the systems he was showing before, which are now a lot more efficient than some of our really old systems. Anyone else?
You're talking about the ground sources. Whenever you go to a bunch of dirt, that there's an opportunity to always take advantage of that heat source. Um, how much heat do you need at all to get some benefit? Because I thought you needed like a geothermal source to have any benefit to a net zero design. You're trying to heat water to 110, 130 degrees. So how much of a temperature delta are you getting out of what's going on the ground?
So at like 12 degrees, at 12 feet deep along the front range, the temperature does not change much between 52 degrees F. When we do a horizontal system, we'll go down to 7 feet, and we can deal with those little bit of temperature variations. So as long as we've got a temperature source that's very constant, we could take that through the heat pump and amplify that temperature. And so that's all the heat pump is really doing. It's taking that 52 degree F and amplifying it to the 120 degrees that we can deliver to the house.
You're using other energy sources to amplify it.
Just electricity through the heat pump compressor.
Electricity as a heat source to add on to.
Electricity's there just to power to turn the just to turn the compressor, which you know there's a refrigerant that goes on in there, so it's a little bit more
So
complicated.
you're using the same heat pump design
Yep,
to take advantage to then leverage that to get it up to the 123 watt.
exactly. We're leveraging that 52 degree F constant temperature.
Like, yeah, dipping into where things are constant.
Yep.
And then using that.
That guy had a question.
Yeah. So, like, can you talk about the market for specifically for air to water heat pumps and being able to use that for both domestic hot water and like radiant heating? I mean, is there a lot on the market for that, or is that growing, or what's that option?
So it's a small market. There's a couple of heat pump manufacturers out there that are doing stuff with that. I can think of 3 off the top of my head. And it's going to be a growing market because we're going to be going a lot more electric. So you're going to see a lot more manufacturers come online with it. So yeah, it's a growing market. Peter.
So, talk a little bit about this transition from kind of the traditional gas furnace to all electric systems. And typically you got production houses, and they're 4,000 square feet, and there's a furnace in the basement, and there's a furnace on the second floor, and then there's 2 compressors outside. When you make that transition to all electric and say an air source heat pump, what are things builders and mechanical contractors start thinking about PLC?
So I converted my production home to all electric using one of the systems that Steve had shown up there at Mitsubishi's.
Yeah, can we steal the mic?
Oh,
sorry.
No, you're good. So repeat that.
So I converted my house to all electric, and I used a Mitsubishi Hyperheat compressor combined with one of their whole house air handling units, and it was a 1-to-1 exchange. pulled out the old gas furnace, dropped in the new furnace, hooked up the existing ductwork, done.
But theoretically, I mean, you could get rid of one of those furnaces that's in the central house. You just do two air handlers, right? In the same heat pump.
I think that gets into the science of developing the load of the house, and back to what Steve said before, which is increase the performance of your building envelope, and then you can start to consider some of these electric options. That's one thing that I do want to point out, that I see a lot of conversation going back and forth with a lot of people in Louisville, where I'm from, that were affected by the fires, that they want to switch from gas to electric straight up without any consideration for the general performance of their house. And my recommendation on that would be, I think that's a bad idea. I think you're going to increase your energy usage. You're going to, or your cost for your energy is going to increase. And those systems are designed different, where they run low and slow, and where a gas comes on and blows a bunch of hot air out and then cycles off and then cycles on again. And the low and slow has a tendency to, let's say, dissipate without much effect when you have a envelope that's not really designed for that system. And we're basically at that point trading one energy source for another energy source without any sort of idea of accounting for our, what's the word I'm looking for, our conservation of resources.
Yeah, remember he talked first about envelope, right? You should talk more about that. But like the link, we've talked about in other sessions, that big link between the envelope, the skin, and the mechanicals, the lungs. You can't separate those two things out. And the only reason we have in the past is that we had really leaky skin.
Yes, there's kind of, I'll unpack your question two ways, right? You said two air conditioners, two furnaces. The reason that is because single phase power, we can only do 5 tons, 60,000 BTUs per hour of cooling in one unit, right? So if your production builder is what you mentioned, so a production builder, they're not really cared about a really good building envelope. So that's why you're seeing the 2 units. You could do it with one if you had a better building envelope and you could get the 60,000 for a 4,000 square foot house. Adoption to market, so a production builder that said we're going all electric probably has the advantage because he can probably train one mechanical contractor really well how to do it on all his systems. Whereas what we're seeing in the industry, there's certain mechanical contractors are really starting to focus in on the heat pumps, and there's certain that are staying in that gas-fired unit, right? I mean, there's still a lot of repair or remove and replace units going on in that gas-fired market, happening all day, every day. Very few mechanical contractors are having a conversation of, hey, let's talk about maybe going to an air source heat pump system and keeping a gas furnace underneath there. There's not, the cost to go from an air conditioning unit to a heat pump unit is minimal, right? A reversing valve costs $30. Cost $100 to put it in a unit. So there's no difference in cost of the equipment. It's just the conversations aren't happening. There's certain contractors are starting to pick it up.
Another excellent side business idea. We've come up with lots today. Local business.
One thing I didn't mention on here, because I was moving a little too fast, with all the rebates, so that we're looking at a house here, with the ground source heat pump system, there's a 30% tax credit that's available for it. And with all the rebates that are in there going to the net zero, I can't remember exactly which level, but it's like $17,000 you can get back by going to that level. And then all electric heating, you get $10,000 back. And then you get a 30% tax credit on the system. That's an instant payback by going to a ground source heat pump type system. So that's another, I mean, the math just works that way out on it. So that's something else to keep in mind when you're doing it, when you're looking at doing a rebuild, that there is a lot of tax credits and a lot of incentives with that.